warahmatullahi wabarakatuh. I'm very happy to we can make a videos, and before we want to introduce ourselves, uh, and then uh, my name is Abdullah, and
my name is Erin dimyati.
Our major is Chemistry and Faculty of Science and Technology. We propose we make videos. I hope our videos we can benefit for.
I will explain to determinant of molar masses of gas and volatile substance. The ideal gas law is used in determining the molar masses of volatile substance. For this purpose, a bowl of volume is filled with the gas at measured pressure and temperature. The mass of the gas in the bowl is measured. Their measurement suffices to determine the molar mass of the substance, where V equal W per V. V is density. Are known from the measurement, hence molarities can be calculated. A rough value of the molar mass is used substance to determine the molecular formula of substance. A rough value of the molar mass is used substance to determine the molecular formula of substance. For example, if chemical analysis of a gas yield an empirical formula CH2, and then the molar mass must be some multiple of 15, 14 gram per mole. The possibilities are 20H, 42, 56, 70, and so on. If a molar mass determination of yield of value affects that the gas is not strictly ideal gas, not as in this collection at all. In this example, the possible values of molarities are well not separated, so that even if the ideal gas law be wrong by 5%, we will still have not difficulty in the assigning the correct molecular formula to the gas. In the example, it is unlikely that the ideal gas law will be in error by as much as 2%. For convenient choice of experimental condition, the ideal gas law is useful in determining the molar masses of volatile substance. Since the determination of molar mass together with chemical analysis establish the molecular formula of gases substance, the results are of great importance. The fact that behavior of a real gas approaches that of the ideal gas as the pressure is lower is used as a basis for precise determination of molar masses of gas. According to aluminum chloride Cl3, Al2Cl6, the ratio of density to pressure should be independent of pressure. Proper V equal molarities per R times T. This is correct for an ideal gas, but if the density of a real gas is measured at one temperature and at several different pressure, the ratio of density to pressure is found to decline slightly under pressure. At sufficiently low pressure, property is a linear function of. And then I will to explain mixture composition variables. The state or condition of mixture of several gases depends not only on the pressure, volume, and temperature, but also on the composition of a mixture. Consequently, method of specifying the composition must be devised. The simplest method would be to state the mole number and 1 and 2 and so on of the several substances in the mixture. The message will also serve. This method has the disadvantage that the mole numbers are extensive variables. It is preferable to express the composition of a mixture in terms of a set of intensive variables. It has been shown that the ratio of two extensive variables is an integral variable. The mole number can be converted to extensive variables by dividing each one by some extensive variables. This can be done in several ways. The volume concentration are obtained by dividing the amount of each substance by the volume of the mixture. The SI unit for volume concentration is mole per entry. We will restore the symbol. This is the symbol for the volume concentration expressed, and the symbol for the volume concentration or molarity. Volume concentration are satisfactory for describing the composition of liquid or solid mixture because the volume is comparatively insensitive to change in temperature and pressure, since the volume of a gas depends markedly on temperature and pressure. Volume concentration are not usually convenient for describing the composition of gas mixture. Molarity are obtained by choosing one the mole numbers and dividing all the others by the one. Choosing and 1 as the divisor, we have RT equal NI per NY. A variant of the Molarity description. The molar concentration M is often used for liquid solution. Let the solvent be confined 1 with a molar mass molar 1. The molarity of component I is the number of molar of I per unit mass kilogram of solvent. Since the mass of the solvent is N1 m molar 1, the number of moles of solid per kilogram of solvent is Mi. And then formula, and next the formula. The molality is the mole ratio multiplied by a constant 1 per mole 1. Since the mole ratio and the molarities are completely independent of temperature and pressure, they are variable to the molar concentration for the physico-chemical dissolution of mixture of any kind. Mole fraction xi are obtained by dividing each of the mole numbers by the total numbers of mole of all substances present. The sum of molar refraction of all the substances in a mixture must be unity. x1 plus x2 plus x3 plus so on equal 1. Because of the relation, the completion of mixture is described when the mole fraction of about one of the substances are specific. The remaining mole fraction is computed using equal to T69 like molarities and molar ratio. Mole fraction are independent of temperature and pressure. The N2s are suitable for describing the quantitation of any mixture. Gas mixtures are commonly described by the mole fraction since the V time T relation have a constant and symmetrical form in the term. Okay, that's all I can see. Next will be explained by Abdullah.
Of states for a gas mixture, Dalton's law. Experiment shows that for a mixture of gases, the ideal gas law is correct in the form V nRT, and then V is freezer and into ATM, and V is volume into liter, and N is mole, and R is constanta 0082, and T is temperature into 2073 and plus Celsius, where N is the total number of moles of all the gases in the volume V. Equation N, the statement of the mole fraction of all but one of the constituents of the mixture constitute a complete description of the equilibrium states of the system. It's desirable to relate the properties of complicated systems to those of simpler systems. So, we attempt to describe the states of gas mixture in the terms of the states of pure unmixed gases. Consider a mixture of the gases described by the mole numbers N1, N2, N3 in a container of the volume at the temperature T. If Nt is N1 plus N2 plus N3 until N, then the pressure exerted by this mixture is given by V and T are T per B. We define the partial pressure of each gas in the mixture as the pressure the gas would exert if it were alone in the container of volume V at the temperature T. Then the partial pressure V1, V2, and V3 are given by V1 is N RT per volume, V2 and 2 are T per volume, and V3 and 3 are T per volume. Adding this equation, we obtain V1 plus V2 plus V3 and 1 plus N2 plus N3 are T per V and N total for RT per volume. This equation with X so that V plus V1 plus V2 plus V3. Comparison of this equation with so that this is Dalton's law of partial pressure, which states that any specific temperature the total pressure exerted by a gas mixture is equal to the sum of the partial pressure of the constituent gases. The first gas is said to exert a partial pressure V1, the second gas exerts the partial pressure V2, and so on. Partial pressure are calculated using partial pressure are simply related to the mole fraction of the gases in the mixture dividing would set of the first of it. By the total pressure V, we obtain V1 per V2 per V and 1 RT per VV. The partial pressure concept. The definition given for the partial pressure of the gases in the mixture is a purely mathematical one. We now ask whether or not this mathematical concept of partial pressures has any physical significance. The result of the experiments illustrated in the figure provide the answer to this question. First, consider the experiment sounds in the figure. A container figure is partitioned into two compartments of equal volume, such as we have, and this is half plus and V and third and 100 and 2 we have hydrogen and V is 50 and we have hydrogen and V is 100 and 4 we have hydrogen plus nitrogen and V is 100. The upper compartment contains hydrogen under a pressure of 1 atmosphere. The lower compartment is equipped. One arm of a manometer is covered by a heme palladium foil and is connected to the hydrogen-filled compartment. The other arm of the manometer is open a pressure of 1 atm, which is kept constant during the experiment is the temperature. At the beginning of the experiment, the mercury level in the two arms of the manometer stand at the same height. This is possible because the palladium membrane is permeable to hydrogen but not to other gases, and so the membrane does not block the extraction of the hydrogen to the manometer arm. The partition is removed, and the hydrogen pill is the intervissile. After a period of time, the mercury level rests in the final position shown in the figure. Since the volume available to the hydrogen has doubled, the pressure in the container has fallen to one half its original value. In the second experiment, the lower compartment contained hydrogen which cannot pass the palladium while under 180 m pressure. At the beginning of the experiment, the mercury levels stand at the same height. The partition is removed and the gases make the target and the container. After a period of time, the level and stand of the partition shown in the figure. The result of this experiment is exactly the same as in the first experiment in which the lower compartment was evacuated. The hydrogen behaves exactly as if the nitrogen were not present. This important result means that the concept of partial pressure has a physical meaning as well as a mathematical one. The interpretation of each experiment is direct. In the first experiment, the manometer read the total pressure both before and after the partition was removed, and phi initial and H2 or T per phi and same 180 m, and phi final and hydrogen or T per 2 volume and 1 per 280 m. Second experiment, the manometer read the total pressure before the membrane was removed and the partial pressure of hydrogen in the mixture after removal of the membrane. The barometric distribution law in the foregoing discussion of the behavior of ideal gases, it has been technically assumed that the pressure of the gas has the same value everywhere in the container. Strictly speaking, this assumption is incorrect only in the absence of the possible, since all measurements are made on laboratory systems that are always in the presence of a gravitational field. It is important to know what effect is produced by in the influence of this field. It may be said that for gaseous systems of ordinary size, the influence of the gravity field is so slight as to be imperceptible even with the extremely refined experimental methods. For a fluid of higher density such as liquid, the effect is quite pronounced that the pressure will be different at the vertical position is container, such as we have and then this is area and A, this is dz, and we have z, and z same 0, and we have G, a column of fluid having a cross-sectional area A at uniform temperature T. This is temperature. Is subject to a gravitational field acting downward to given a particle and the acceleration g. The vertical coordinate z, the measure up from ground level where is z same known. The pressure at any height z in the column is determined by the total mass of fluid above that height. The downward force on this mass is mg. This force divided by the area is pressure at the height, and phi same mg per a. The differential equation relates the change in the pressure dV to the density of the fluid, the gravitational acceleration, and the experiment in the height dz. The negative sign means the if the height increases, the pressure of the fluid will decrease. If the density of a fluid is independent of pressure, as in the case for liquid, then may be integrated immediately. Since rho and g are constant, they are removed from the integral and we obtain, such as we have integral and phi 0 until phi and d phi and rho g, or 0 until z or dz. With integrating gives phi mean p null and mean rho g z, where phi null is the pressure at the bottom of the columns and phi is the pressure at the height z above the bottom of the column. Equation is the usual equation for hydrostatic pressure in a liquid. To apply to a gas, it must be recognized that the density of the gas is a function of the pressure. If the gas is ideal in the form rho same m phi per RT. Using in this equal, we have d phi mean mg phi dz for RT. Separating variables yields d phi for phi and mean mg dz per RT, and integrating we obtain learn phi mean mgz per RT plus c. The integration constant c enabled in the term of the pressure at ground level. When z same 0, phi same 0, using the dash value in, we find that learn phi null same c. Substituting this value for c and regarding the radius. Since the density is proportional to the pressure and the number of moles per cubic meters is proportional to the pressure, can be written into other equivalent form. And I say thank you very much for watching our video. And to Allah, I say I'm sorry if my explanation is I have some mistakes. And if you want to question about physical semester, you can comment for under. Okay, thank you.
Don't forget to like, subscribe, and share.
Wassalamualaikum warahmatullahi wabarakatuh. I'm sorry. And
and then you're watching.
Red cups and sweaty bodies everywhere, hands in the air like we don't care, cause we came to have so much fun now. Got somebody here might be the one now. If you're not ready to go home, can I get a hell no? Cause we're gonna go all night till we see the sunlight, alright. So la-da-dee-da-dee, we like to party, dancing you and me, doing whatever we want. And this is our house, and this is our rules, and we can't stop, and we won't stop. Can't you see it's we who own the night?